Okay, so okay, so the final session today, we first have Professor Heng-Yu Chen from NCTS, and he's also coming to items in September. He will stay for how many years?
A few months.
A few months, yeah.
Right.
Okay, so the title is Comments on two-point functions in terms of CFT and holographic.
Okay, so thank you for the invitation to this nice workshop. Okay, so today I'd like to talk about some, ongoing work and also some past work I've done with the two group of collaborators, and some of them were affiliated with weekend in their previous career. And I think actually I was looking at the kind of intensive lecture list. So Hatsuda-san will give some background about this topic, like in the coming class the weekend as well. So this is actually something like I've been trying to work with this bunch of collaborators and trying to understand that what the holography will actually tell us about some feature about the thermal conductivity and finite temperature. Well, actually, probably closer to my heart would be like what does the finite temperature field theory, and based on some very general assumption that will actually allow us to understand what's happening in the okay in the bulk physics. So okay, so and hopefully I get to talk about some of the ongoing work I'm trying to finish. And please do stop me at any time if there are some questions. So let's kick off with some general statement about how I guess some of you like working on condensed matter theory, and some of them working on high energy, and probably come across some basic result in the so-called conformal field theory, where the scale invariance, and actually I'm going to focus on in most of this talk in the relativistic version. So when the scale invariant kind of manifest, but probably haven't come across as much with thermal, conformal field theory in the case of finite temperature. So I guess probably this even sounds a bit like some kind of misnomer, but let me try to kind of expand it a little bit about what I mean by that. So usually when we learn about conformal field theory, that, for example, based on the conformal symmetry, and especially the spatial conformal transformation group, that we would establish a statement that, for example, if you consider basically the kind of fundamental primary operator, so these are kind of fields operator that depends on different local operator, depends on different space-time insertion points. Now, if you calculate the expectation value, then these things will identically vanish unless this is actually identity itself. And so that was that. And then the second things, like if you open any conformal field theory lecture notes, then you will learn about, for example, like the zero temperature, that if you calculate a two-point function, there's not much to calculate, really. It's actually kind of parametrizing using one of the important data in the conformal field theory known as the scaling dimension, which basically then tell you that what are those operators that, as a space-time coordinate change the sizes, and how are they going to weight it with your scaling factor. And they have to be orthogonal to each other, and meaning that if you are considering the two-point function among conformal primary operator of different scaling dimension, these things should vanishes identically. Okay, so I'm going to stop here. So at the two-point function, because actually there's already quite a lot of interesting physics, and in fact, for those of you who know a higher point function, there are actually more symmetries that at the finite temperature, at the zero temperature, that which allow you to constrain them further. Okay, so if we want to turn on the temperature, we want to heat up the system going from zero temperature and then make it closer to our real world, what can we do? So usually in the statistical mechanics, what do we do? That in the partition function, then what we would do is that first we would try to, for example, instead of working in the Lorentzian signature, and we will try to basically perform a weak rotation that go into Euclidean signature. And next thing is that in order to make things at the finite temperature, we will try to compactify now this a new Euclidean time at the periodic circle, and the period of this Euclidean time then basically is proportional to the inverse temperature. So we try to perform this in the study of conformal field theory systematically as well. And the first thing when we are doing this, then you notice that there's something very different is happening here. Is that precisely that when we are considering, for example, there's a size of a finite circle, then that naturally introduces scale into our problem. And that scale, we call it a beta, or the inverse temperature. And the first thing that modify our basic knowledge about the conformal field theory in the finite temperature is that now the one-point function is no longer vanishing in general. But on the other hand, that is actually going to be, well, as you might be able to guess it, if it's scale as a scaling dimension delta, then how the things, once you have a natural scale, this thing should actually scale as beta to the power delta. And there are some coefficients which are independent of delta, and there are some indices that, to get a tensor structure out. So we can generally consider this type of operator. And this has interesting consequences, because now if you actually now study the two-point function now, and two-point function, what should you be thinking about in any quantum field theory lecture courses? Based on the locality, you have when you bring out those two operators very close to each other, then you can think about them trying to expand them, expand the two-point function of those guys in terms of whatever possible other field theory operator exists in your theory, and literally doing like a kind of similar to Taylor expansion out of it. And but for conformal field theory previously, you will see that, well, all the one-point function enters here, then this thing actually vanishes, and this thing's actually, in fact, after some algebra, you will convince yourself that this thing's actually only basically give you back to the orthogonality condition. But now precisely that, we are modifying at the finite temperature. The one-point function now takes this a very complicated form. Now at the two-point function, we already have an interesting structure compared with what you may have learned about the zero temperature conformal field theory, that in fact three-point function can also be fixed by the conformal symmetry. And the only interesting structure that when you have a different kind of unknown actually happens at the level of four-point function. But at the finite temperature theory, actually, there are some interesting structure that already appear at the two-point function. So let me try to kind of unpack this notation a little bit. So we are studying now at the finite temperature the two-point function involving two, just make life simpler, involving two identical operators that carrying the scaling dimension delta phi. And this expansion is telling you sometimes referred as an OPE expansion in the conformal field theory. Now it depends on some data. One of them is actually the OPE coefficient, which normally previously we think about it actually associated with the three-point function. And what are they between? Between those operators, delta phi, and all the other possible operator exchange between them. And then also the scaling dimension of a particular operator exchange among them, delta and the external guy. And everything else here actually fixed precisely by the your conformal kinematics. And sometimes they are, well, this guy is actually a Geigenbauer function. If you write down any spherical harmonic that actually appear, but it's some kinematical information. So this is basically, for those of you like in notes, then you can regard this as a kind of analog of the the OP expansion of a four-point function. And next thing, what do you think about four-point OP expansion? Well, it doesn't matter. Actually, it doesn't matter how you actually take the OP product between different pairs of the operator in your correlation function, because there should be something known as a crossing symmetry. And you wonder, like in the two-dimension, what's actually happening? Well, this condition was actually figured out by actually K, I think, stands for Kubo. I can't never remember MS who the Espo stand. There's a very famous Japanese physicist. The analog condition here is actually that, remember, this thing was, how do we obtain this guy?
this guy will actually obtain it by putting a periodic time, Euclidean time here. So basically the similar crossing condition here is actually precisely that when you're shifting the tau by its one period, this thing should actually get back to itself. And from the kind of like complexity of this equation, now you can see that if the tau actually naively just shifting in this entire sum, like by the term beta, then you will see that, well, in order for this equality to be satisfied, and in fact, this is not going to be, mathematicians usually have enough number of equations and give you enough number of variables, but actually only given a constraint that allow you to actually put in a constraint on, for example, the value of the OPE coefficient and the value of the possible exchange operator. And this sometimes goes along the name of a thermal bootstrap equation. And recently this has played quite, there's a kind of active field that people are using this kind of bootstrap equation to study finite temperature field theory. I guess this is like, another, for those of you who are playing those games, this is another epicycle that people previously considered finite temperature CFT, then that would be like, especially in high-energy theory, they will consider things like, ADS condensed matter, and then previously ADS QCD. So this is another epicycle in this game. But of course, there are a lot more new technology that which has been developed over the past 15 years or so, like in the kind of zero temperature conformal bootstrap program. And what people have been doing is actually trying to use what we learned about here and generalize in this setup.
Question.
Yes?
Why is the shift by, not by plus beta, but you have somehow conversion?
Oh. I think that's just a matter of convention that you could actually do it. You could actually do it like, well, I'm kind of imposed there. Also, there's a symmetry that which, going reflection between the tau to minus tau as well. Good. So I'm basically putting this into this construction as well. Yeah, there's an extra constraint for this tau to minus tau. Good. So that's, but still not enough constraint. The key point here is that it's still not enough constraint to constrain your value of those. In fact, the whole game, you can actually try to just expand it a little bit. I probably won't be able to get through all the slides, but who cares? That you can actually even take this to the other side, take a derivative with all this, for example, all this spatial coordinate. That has to equal to 0 as well. That gives you additional constraint. So naively you think, oh, there's one constraint. There are, in general, infinite number of parameters over here. Is there any chances? Yeah, but it turns out that by, there's a series of differentiation, and in fact, that's what people are also doing for the case of zero temperature bootstrap. They have actually generate infinite number of the differential equation and also infinite number of variable. And in fact, what is really actually happening later on is that, well, you generally will have an infinite variable, infinite linear algebra problem, then you have to invert these matrices. So you have to make a truncation, and that becomes a computer power. And that basically connected to what people usually know. Well, actually, this doesn't have quite a semi-definite programming structure. In fact, to make it, for those of you who know, that if you have a unitary CFT, then you will have a OPE square here. This will be positively definite. So this is actually another contrast with the zero temperature. That you don't have that particular structure even for unitary CFT. So, but in general, it's have many equations. So that's a computational intensive problem. Luckily, I'm not a computational guy. I'm a holographic guy. I try to cook out with a toy model that make my life a bit easier. So, so one of them, and that's one of the motivation why I care about this kind of thermal two-point function, is that through the kind of ADS CFT correspondence, which unfortunately I won't have time to mention too much about, because tomorrow there will be some talk about holography, I imagine. That actually allow us, for example, related, just for the things like to get some like bluffer's line, that basically this whole computation of a quantum field theory living in the d dimension, living on the boundary of some curved manifold, which basically can view that as a higher dimensional Pringle, in a one-dimensional higher, that everything you know about this quantum field theory, holography is true, could actually be encapsulated by the appropriate computation inside the bulk. And this is one of the earliest computation that people, 25 years ago, that people were trying to do to verify the holography, which basically allow you to actually map the computational two-point function on the boundary field theory at a strong coupling with the something very similar like you do every day in the quantum field theory, doing the kind of Klein-Gordon equation. But now this guy is actually your D'Lambertian is actually now the de Sitter, the anti-de Sitter Laplacian instead. But you have to solve this equation, and with some Thorsten. So, and this computation, basically what does it yield you? Well, if you actually, so let me kind of unpack a little bit. So here, x1 and x2 are basically, we're looking at the two quantum fields that are propagating in the d+1 dimensional ADS spaces, that which are living at the boundary. And if you probe this side in the ADS, basically the radial direction of ADS are given by the R here. So you are basically studying a field in one dimensional higher, so you are solving this differential equation. But now if you actually push one of those coordinate in the particular choice I make here is something known as a Poincare patch to the let me get this right. Yeah, to the Poincare patch. Then this actually, in the coordinate choice I made, is actually going to the R to infinity. That allow you to actually recover the corresponding the field theory two-point function we look at. And what does correspondence means? That simply means that masses that associated with those bulk field are precisely going to be given by going to map to the operator of the same scaling dimension. So that was the law was generally for finite temperature. But what people can actually generalize this again is actually to the case of higher to the zero temperature, and this can be generalized to higher temperature. And we're going to look at the actual geometry later on. But let me flash out just what a general strategy in people trying to do here is that. So we would generally assume, just like when we solve any partial differential equation we teach our second-year undergraduate, which basically allow you to making some ansatz, like some spherical ansatz, some radial coordinates. We're going to focus on radial coordinate and also a time coordinate, whose eigenvalue is going to give you the basic related to the energy. So once you bang those ansatz into solving this equation, and you can perform this coordinate transformation in the GR literature, sometimes known as the tortoise coordinate transformation. And in this, we give an explicit example of, for example, for the ADS Schwarzschild black hole. So this is actually like the kind of curve space generalization of a famous Schwarzschild black hole, now asymptotic ADS spaces. Now we could actually turn the whole equation, this whole business about solving the propagator equation we had earlier, into basically Schrodinger equation with a potential given by the following, and the omega given the eigenvalue, and all these parameters can enter the problem. So the task is actually trying to solve this. And now, of course, conversely, what does this buy us before we actually get into the mathematics here is that this is going to buy us by solving this kind of different kind of differential equation that actually allow us to, for example, know something about boundary field theory. But if you believe this correspondence is true, and we're going to try to argue that later, then for different kind of, so this actually also allow you to study the finite temperature and the boundary, and trying to know something about different geometry deep inside the ADS spaces. So, but first thing first, in order to actually solve those equation, we need to impose a boundary condition, second order differential equation. So there are these are two different solutions that satisfy different boundary behavior. And so we impose this as a boundary of ADS. And if we have a view in a black hole, actually deep inside the ADS, we should also have basically the ingoing boundary condition, because black hole nothing comes out. Of course, there are things going to debate about that one. So. And basically, the dictionary of ADS CFT, and this one was actually proposed by Starin and Song and Kofton, I think like 20-something years ago, was actually, by doing this kind of computation, studying the asymptotic behavior, like where the coefficient are actually controlled by the A omega and B omega L. L here is the angular momentum piece, omega is the frequency. We can actually obtain something very close to the Euclidean thermal two-point function we had earlier, which is basically sometimes known as a retarded Green's function, and it's actually related to the Euclidean two-point function in the frequency spaces by the ratio of these two. And basically, in order to get back to the Euclidean Green function, then you perform basically a Fourier transform, and also the angular part, you also do exactly the same thing. Then the next question you want to ask is that, what are the dominating contribution in this? And what you do is that then when you do a Fourier transform, you want to consider this as a complex integration. In the contour integral, what's the most important thing? Well, where the poles are. And the poles actually precisely going to appear when basically when at a very special value of those frequencies, when the omega, where the A omega, which this function will be given later on, actually contains the 0 here. And then that will basically, the residue will basically give you the whole answer of this. And if you transfer back to the position space or time space, in this case going from omega to time spaces, this basically allows you to write down a Fourier transform of this object that in terms of a different kind of those special value of frequency, and that it carries the name of somewhere which I erased it, but this thing is actually called quasi-normal mode, which is something basically in the study of the perturbation of a gravitation of different gravitational background. This plays an important role. You may also say, just to bring this to a closer language to what we usually think about, perturbation in a gravitational series, that for those of you actually study GR, like at the undergraduate level, you should know that, for example, doing basically tensor perturbation of any given background, once you decompose into the the tensor mode, vector mode, and then finally there's a scalar mode. That scalar equation over there we are writing down. It's precisely the scalar equation that basically perturbing around the ADS black hole geometry. So that's what we are solving, and then that's where the frequency, the quasi-normal frequency is actually going to give you. Good. I have 7 minutes to actually finish up what I want to say. But let me talk about some feature about what we can do about this, and why is something special about holography compared with the general game that we are studying other kind of correlator. So one thing is that basically for all this kind of holograph, so in general, yeah, maybe a probably more profound statement or more interesting statement here is that, yes, so there are many different kind of thermal conformal field theory, but not necessarily all of them actually have the so-called ADS bulk dual, not having a geometry like black hole dual to it. And one of the features for this class of two-point correlation function is that they actually contains what's known as the Balcon singularity. And this is something different. So usually you expect, what do you expect here? Well, I mean, when you look at this kind of two-point function, you expect that, especially in the Lorentzian signature. Well, you can see that in the denominator, there's going to be something depends on separation. And clearly, well, when the separation goes to 0, the separation becomes line on the boundary, then the whole thing vanishes. There's a usual Lycon singularity. But in addition, the point here is that in addition to those singularity, which we don't normally expect from the normal thermal, even quantum field series, that there are additional those singularities appear at the coordinates which we don't normally expect them to happen. And they should have a nice interpretation for it. And in fact, for the class of a series which actually have this bulk dual, we could actually see very clearly and understand their origin. So back to, for example, so how do you understand this? Well, the simplest case people can calculate is that when we think about a special class of an operator where the scaling dimension is very large, and that really corresponds to in the ADS spaces that we are looking at a very massive particle and moving along the geodesic in the geometry, that the quantum mechanical problem remains the same. But we could actually use this very kind of classical kind of geodesic type of approaches to actually work out. So delta here is, dot here is basically the affine parameter your geodesic, solving for the time coordinate, solving for the angular coordinate. And these are basically some non-geodesic which we could actually also write down. And finally, we can solve the chord length, which describe what? Describe living on the boundary of series. You have two operators inserting at the 2 point, but then there's a chord for your particle now, which basically moving along with the chord length connecting the two boundary points. And the chord length here, basically precisely according to holography, give you the 2-point function. And what do you see here? What you see here is that, well, so basically the 2-point function actually develop a singularity by this computation now at the t equal to this t node, which we can actually write down explicitly. But the key point here is that this is not theta. And why is it not theta? Because if there's t equal to theta, this is actually precisely like, if you draw out your light cone on the boundary, that's where the things that, living on your light cone. That's your light cone singularity, but the additional guy is actually right over here. So that's a feature of this. So I have 5 minutes. Let's change the gear to talk about, let me see, what would be the right thing to do? Yeah, since there are some math and some physics, let me talk about some physics. Maybe let's talk about some math, then come back to talk about physics if I have time. So another approach that which recently has become quite popular that to solve this class of quantum mechanical problem, this might ring with some mathematicians as well, is that, well, actually, if you open any of the, the OGR homework book, actually, I think I looked this up before by Price or something. In fact, that quantum mechanical equation, in fact, apply to many different black holes you can write down. You can imagine now you can go where setting your used to be student and now it's ChatGPT and now this slide is handwritten, so it's actually written by human, thankfully. But for different class of black hole, and in fact, that not just asymptotically to ADS spaces, but in fact originally to the flat spaces, and recently there are people looking at the case for de Sitter spaces. You could basically, writing down the radial equation for the scalar perturbation and the package into something looking like this. And of course, and this equation, if you going back into any ChatGPT, then this will tell you, this equation looks something like a Heng equation. And of course, there are special cases, it depends on your different geometry. So all these coefficients, alpha, beta, gamma, delta, will depend on precisely what kind of black hole you have, and depends on the masses, and sometimes even later on, we're looking at some cases for the angular momentum. So what can we say about it? The next thing, what do we think about this kind of equation? Well, again, it's a second order differential equation like the one we had before. And this second order differential equation actually contains a singularity, and there are 4 of them. We can even read it out from here. It's as precise as z equal to 0, z equal to t, and z equal to infinity, and also z equal to 1. There are 4 of those singularities. This is a general Heng equation. And so to solve them, in fact, you can only solve them patchwise because you need to avoid those singularities. And you can only impose a boundary condition that for those differential equations around the particular singularity. And when you go to different patches, then the boundary condition will change it. So focusing on, for example, z equal to 0 for this class of equation, there are 2 independent solutions have a very different behavior. So one of them is actually the kind of regular behavior, and the other is a singular behavior. And what's the point of talking about this? Well, let me bear with me one more slide here is that, so if we go to different slices, then okay, so what we can do on the other hand, just like, for example, when we're dealing with a hypergeometric function, we want to perform a modular transformation. But in practice, what we are really doing is that it's trying to expand, for example, a solution in the, around the other singularity in terms of what you had before, but then provided you know how to join them. And this is basically something known as a connection coefficient, but it's just a fancy way of what we teach the first year undergraduate, that writing a wrong scheme and then trying to for the basic solution and then write them down. But it's easier said than done. That's the problem. That's the real problem. Now all these are very nasty. If you look at the Heng equation, ask Mathematica to cook it out for you. This is actually not very nice. So what's the deal about this? So the recent development, and this is related to one of the things I'm finishing with Ishii and Ishikawa and also Hatsuda, is that actually, what can I say? The recent development is that physicists realize that, well, this mathematical problem can actually have a very nice solution to it. Basically finding out those connection coefficients. And it turns out there's a very convoluted way which I'm happy to explain in private. Is that Heng equation, if you go and unfortunately look at your big yellow book, like from the Senegal and wherever, like all the condensed matter people now, they also try to read those. These students try to. You realize that, well, there's a classical conformal field theory called WZW model, and if you look at the 5-point function, it inserted a degenerative vertex operator, and which later those to do with N-Yon. Those things actually are constrained by the differential equation, and those things are precisely the Heng equation. And but the recent development is that people realize those Heng equation can actually be mapped to basically the partition function of certain class of 4-dimensional n equals exponential gate theory, blah, 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 blah. But then the punchline is that we could actually try to write down, the one message here is that we can write down those connection coefficients in terms of what we know through the 4-dimensional supersymmetric field theory using some technique called localization. And what's beautiful about this? Well, it's still not very beautiful, but the things are when you punch those, what do we care about? Because once we map those solutions to our previous business was that one thing we care about is, so this is one slide of telling you how to mapping the parameter. But one thing you can take away is that once you know this could be one of the incoming condition. This is outgoing condition. This is your A, this is your B, let's say. If you know the explicit expression, you could actually solve what the zeros in the A actually are. And why is that telling you? Precisely where the location of quasi-normal mode actually are. And this actually apply, this technology actually apply to wide class. So this, this was actually noticed by Hatsuda much earlier. And so this is the equation supposed to mean that we are trying to solve this. So you can actually get a machine to actually invert this, to find out what the quasi-normal frequency associated with the participation of ADS short-charge black hole in general D-dimension. And in fact, this technology goes on, and this is one slide talking about what how we go on for this work. That you can even consider rotational analog of this ADS black hole, sometimes known as a Myers-Perry black hole. And I only recently learned, for those of you learning about Myers-Perry, don't call it Myers-Perry because it was actually found by Marika Taylor instead. So you should call it Marika Taylor black hole, and Myers-Perry is the flat space of this game. But anyhow, so in this case, you make an ansatz, solve the equation. You can again show that the perturbation equation around it is actually given by Heng equation that we could actually solve very nicely the frequency, and more importantly, the significance of this. Yeah, just to wrap this up, the significance of this is that previously we have to make this rotational symmetrical ansatz and then band this thing, but actually you don't necessarily have to. You can actually, even this correspondence with Heng equation, go beyond the rotational black hole geometry, then you can actually have a kind of additional rotational correction to it as well. So there we are. I gave about half of a talk. So I missed out the middle part in the WKB. So, but I guess for the iTHEMS crowd, Hatsuda-san will be there in a couple of weeks. He will talk about something like this. And so there was actually a very nice complementary approach. Yeah, so I can even probably, no, I shouldn't be annoying to each other, it's late. So you can imagine now in quantum mechanics, we're trying to, another way to phrase the problem earlier is that this is basically a quantum mechanical problem. There's another way of solving this complicated potential, which is the WKB approximation. And then we can apply this WKB approximation to various kinds of potential as well. And there's a very nice technique that associated with quantization of the periods in the WKB approximation that allow you to solve those quasi-normal frequency. And then we can get a complementary answer to these two different things. So, so what's the message I'm trying to convey here? Well, I guess this conference is supposed to bring the computer science mathematician and the physicists together. And usually I'm focused on one corner and not the other. But this is one topic that I think this is a very, very nice, area that for those things coming together, and hopefully, like using this as a platform between NCTS-iTHEMS and regularly. Initially, probably nothing come out, but as the time we progresses, and hopefully we will have something fruitful through the collaboration. So I end here. Yeah, thank you. Yeah, Chen, yes.
What is the connection between these saturated parameters and temperature you mentioned in the theory?
Yeah, so basically those things later going to be written. Yeah, yeah, I mean, absolutely. So, so for example, in these cases, I make it very small because no one cared usually. So this is actually to do with, so I can read it out for you. This is for Schwarzschild, there's an inner and outer black hole. And so you will have, it's a ratio of outer black hole versus with the differences of the outer and inner black hole. So yeah, I guess you can translate that into temperature later on once you, right, you know, just recast everything, horizons and all that. You can rewrite it if you want to. But one thing should be said, and I think that probably can be said, is that the temperature on this black hole here is not necessarily the temperature on the boundary theory. And in fact, we know that because beta is over here. This is actually the real. Oh no! I'm being stupid. No! This is not. I'm talking nonsense. It's different beta. It's just a beta parameter in the specifying the equation.
So this the point equation has 4 singularities.
Yes.
And so one is so 6 well. So 3 singularities you can fix 0, 1 but
yes.
Here you cannot. So you have a moving singularity.
Yeah, that's right. You have this accessory parameter. Yes.
So basically, what does it mean?
Well.
Yeah.
Well, so actually, that's a funny part. So actually, those singularity actually, you know, become, yeah. So for example, we can give an example. Right? I mean, just in terms of those parameters. So how do we remove one of them? Well, setting one of the, you know, gamma, delta, or epsilon to 0, right? That will remove one singularity, and that's easy. So you will, for example, let me see. So if I could get this one right. So, blah, blah, blah. So for example, let me try to epsilon. Yeah, this is writing in a funny way.
Yes, in the case of where 3 singularities, where the variance properties are given in terms of the holonomy around the singularity.
That's right.
In this case, where so even though the singularities are moving, but the holonomy is invariant under the shift of.
Yeah, so you're shifting them. That's no problem. Yeah, shifting them. But I'm trying to say is that actually in the yeah. So for example, if you what can I say? Yeah, so for example, in the case of extremal black hole, that if you have a charge, yeah, actually that's a good, I didn't turn on the charge here. So if you have a charge and mass equal to each other, that's an extremal black hole basis. Some singularity actually get killed as a result. In fact, it becomes confluent home equation instead. But happily, yeah, maybe if I allow to. So what's really nice about the recent, you know, AGT inspired, we can talk about detail later. But there's a data point in the series of paper by the Trieste group, by me, by Nandini, and other people, was actually that for all these different, so it's very kind of math script that you, for different classes of a home equation, you could actually, so the connection coefficient for all of them. And that allows you to, so your job is actually trying to first see if your perturbation equation can be fall into class one of those guys. And of course, to solve for the pole, which I gloss over the detail, and then that's when the graduate student become useful, is that we actually also have to, invert a nonlinear equation, like in the original cycle-Witten series is known as the Riemann relation, which, roughly speaking, boils down to inverting obtain an argument of a hypergeometry function. So then once you plug in, then you can go order by order in solving the frequency. So it's not like it's like a cure for the inflation or like world disease and all that. But it gives a systematic way of obtaining the equivalent normal business requirements.
Okay, so thank you very much.
Yeah, thank you.